Hello everyone, hello and welcome back to AI Tuesdays. My name is Erika and I am the program manager at MicrosoftReactors.com. Today we are going to kick off with season 2 of the AI and machine learning track in the Championing Azure Collection Series. Before I carry on, I just would like to say a quick word about Microsoft's Code of Conduct. We all come from different backgrounds, but we are all here to learn. So please be aware of each other and be welcoming and respectful to all points of views. Thank you. Now, I would like to introduce you to our speaker today, Alan Smith. If you have been following season 1, Alan is a very familiar face by now to you. But if you don't know Alan yet, he's an Azure MVP, a software engineer, a developer, a mentor, a community leader. And once he has also been recognized as one of the top 10 developers in Sweden. And I think he's also been the MVP of the year a few years back as well. In this demo intensive session, Alan is going to be, we will begin with showing how a single neuron can be used to predict apartment prices. And then extend this basic model to a full neural network. By the end of the session, you will have a solid understanding of neural networks and understand the difference between sigmoid and the leaky riddle. This session is going to run for about 40-45 minutes, and we will have some time at the end for questions. But now let me bring here Alan. Hey, Alan. Hello.
Hi there. How's everybody doing?
Yeah, thank you so much for being back.
And, it's good. Yeah, it's nice to have a quick break, but then it's good to be back.
Exactly. I mean, we had a week, 2 weeks break, but now we are back, and you are here today and the next week as well, right?
Yeah. So next week's going to be StarCraft AIs, I think, which is going to be fun.
Oh, nice. So yes, thank you so much for being back. I'm going to just, as you know, I'm going to put myself to the background, but I will be here listening if I'm needed. So I see you soon. And guys out there, ask your questions, please, in the chat.
Yeah. I'm watching the chat as well, so please feel free to do that. Yeah. So good evening, good morning, good afternoon, depending on where you're from. My name's Alan Smith. I work for a company called Active Solution, and what I'm going to be talking about in this session is taking a very basic introduction to neural networks and then pushing that, basically running through, increasing the complexity level, and then getting into generative AI. Disclaimer, I can't dance as well as this animation. This animation has actually been generated by one of the AIs that I'm going to be discussing. You can tell, the artifacts don't look that great, but it's basically a generative model that I've used. It's actually Bruno Mars who's done the actual dance moves, and I've kind of sampled those dance moves and then mapped my image onto those moves. And that's something that kind of really interested me when I started looking at AI and the different scenarios you can work with AI. I was browsing around on YouTube and I came across this video. I think I've actually got in the browser. I've actually got the full video, which I can show hopefully. And it was a project that some students were doing in the US. I think it was Berkeley, and what they were doing was they were sampling. I was taking a video of somebody who can dance, and they were using pose detection to be able to figure out the actual poses. So this is basically it's an AI model that does the same thing as Connect does. It can basically analyze this image, and it can give you a stick image. And then from this stick image, they can take a video of somebody who can't dance, maybe can't dance professionally. We can actually map this dancer's movements onto this person's movements here. So you can see the actual source video or the target subject. You just basically have to make a few moves, and then once you actually do the mapping, it does come out very convincingly that they are actually following those moves. And that just completely blew my mind. I just thought, well, how can you do this? How does this work? What is the maths behind this, or the the computer science, or the data science behind making something like that? It just seemed like magic to me. So I sat on a quest to be able to figure out, how to do this and how to be able to create one of these videos and get into a generative AI. But before we get there, we've got to really start at the basics and start to look at real basics of how things work. I've discussed previously about the what I term as the 5 levels of AI development. So we can work at the application level where we just don't know anything about programming, a user interface, and we've got AI built into our services. We can use the cognitive services that we've talked about in previous sessions. Peter Ernholm's a real expert on that. We can work with things like custom vision and machine learning studio, where we take responsibility for training the models. And we can work at the framework level as well, using libraries like PyTorch and Keras and TensorFlow and so on. We've also got the option of jumping down into the algorithm level and actually understanding the nuts and bolts of the algorithms and how those algorithms work at a basic level. So I'm going to be working mostly at the algorithm level, jumping into the framework level a bit because I've got a bit of code that is using PyTorch, and we'll take a look at the everybody dance now code if I can bring up some of that. So probably the simplest thing you can do, I think I've covered this in a previous session, is basically linear regression. So you have a series of points, and what you want to do is to estimate, whereabouts these actual points are going to be. Typical example I use is, how much is an apartment in Stockholm based on the number of square meters that apartment occupies. So what you can do is you can estimate a line, and you can calculate the loss between these. How far away are these predictions from the actual true values? And the idea is to basically optimize the algorithm so you minimize the actual loss. It's never going to be completely accurate because there's so many other factors involved in this, but coming out with some kind of linear expression for this. Now we can do this with basically one brain cell of a neural network, which is known as a neuron. And a neuron basically does a bit of maths, and it basically calculates a straight line algorithm. So if the input is 0.8, we have 2 parameters in the neuron. One of them is called the weight, which is 0.5 in this case, and the other parameter is called the bias. And the formula that takes place in the neuron, we take the input, we multiply it by the weight, and then we add the bias. And that gives us a value of 0.7 that comes out of the neuron. Now, it's possible to do linear regression using a single neuron. The line here is y equals mx plus c, and we've pretty much got that formula within the actual neuron. So the neuron on its own can basically figure out this linear regression. So first demo, I'm just going to show how this works, if I can find the actual solution. And I'm basically using PyTorch for this demo. And I've built a neural network in PyTorch that only contains one neuron. And the actual data that I'm using to train it on is apartment data in Stockholm. So this is my apartment price data. And what I'm doing is I'm just basically filtering the data. And the only fields I'm taking is the price in Swedish krona and the area. So if I run this application, it will basically show us the top part of that data set. So we've got some prices and we've got some area. It's about 10 euros per dollar or per pound or per euro, 10 krona per dollar, pound, euro. So about 3 million krona is about 300,000 pounds, basically what it costs to live in Stockholm. And these are the areas currently around where I live. So what we're doing is we're basically converting the actual prices into smaller digestible values. You could argue that the price is an integer, but it should really be a floating point value. And what we're doing is we're using the standard deviation and the mean to basically normalize the data. Neural networks don't like it when you give it 3 million as an input. It likes to have something plus or minus 1 or something like that is a good value. So by using the mean and the standard deviation, we can basically normalize the actual data. And what we can do is basically train the neural network over a number of iterations to be able to predict the apartment price. And this shows us the actual loss. You can see that as we go through these iterations, the loss decreases and then it starts increasing a bit, which is fairly typical and probably shows that my network is overfitting a bit. And then this is showing the prediction that I've got and the actual price based on some data. So my model is really overestimating a bit the actual prices of apartments. And it's giving us the neuron weight and the neuron bias, those two values, 2 parameters that it's optimized, and it's saying enter the apartment area in square meters. So if we go for a 50 square meter apartment, it says that that's going to cost about 3.18 million krona. If we go for 100 square meter apartment, it comes out with 5.6 million krona. I think the data is a bit old. It will probably cost a bit more than that in Stockholm today. So the data probably needs updating. Interestingly, if the apartment is 0 square meters, it's going to cost, predicting it will be 764 million krona. So that's maybe a premium that you pay for living in a particular area. And going back to the slides, if you whiz back a few slides, if you think about the square meter price per apartment, and that's the only thing you're using, the line would pass through 0, but it doesn't. The optimal line basically intersects here at this actual price. So with 0 square meters, you do have a certain price on that. So we're going to get on to looking at more complex scenarios now, and working with more complex networks. And I'm going to start off, speaking to, what I was probably 2 years ago. I was a programmer who dealt with zeros and ones. So when you're doing logic in a computer program, you're dealing with bits. I trained as an electronic engineer, so I'm very familiar with the 7-segment LED display. And, we used to have exercises where you use AND gates and OR gates and stuff to, actually drive these displays from counter chips and things like that. So what we can do is you could actually build logic that decides that this, or predicts that this is a figure 6 based on whether these actual segments are lit up. So if you're going to write that in, pseudocode, it would look something like this. You've got the A, and then B is off, so it's not B, and we've got C and D and E and F and G. And that basically means that the number is going to be 6. And you could write another sort of 9 lines of code like this to be able to do predictions for the other numbers based on whether those segments are going to be on or off. So when we get into machine learning and neural networks, we've really got to get away from the idea of thinking of ones and zeros. What we're doing is we're using floating point numbers to come up with a probability if, this is going to be a 6. So what I've done is I basically said, well, that's the figure. It's not ones and zeros anymore. Now it's floating point numbers. The display is, 10 or 15 years old. It's not that great quality. Sometimes when things are off, they look like they're on. Sometimes when they're on, they're not shining too bright. So how do we actually write the logic now to be able to predict what number that is? You could say, put a threshold in if it's greater than 0.5 or whatever, then it's going to be considered on. Or you could use a neuron to be able to do that calculation with a number of inputs and being able to actually predict the actual output. Another thing that we like to do is just stick on what's known as an activation function. This is known as a sigmoid activation function. Because the neuron could give an output of, say, 15 or 8.5, we'd like to have that value between 0 and 1. So the sigmoid function will just basically put bounds on that and make it between 0 and 1. And there's a number of other activation functions we've got, such as relu and leaky relu and tan h and various things like that. Sigmoid was used very commonly in the early days. Other people are using more sophisticated functions there. So what we can do now is we can use a neural network to solve this problem. So what I've done is I've got my inputs, and each input of these is coming from one of these segments in the 7-segment LED display. And then I've got my outputs, and the output is going to be a prediction. Is it going to be 0 up to 9, those actual digits there? And by basically putting in all of the parameters we've got to configure, that's showing that 0 is going to have to consider all 7 inputs, 1 is going to have to configure all 7 inputs. And each of these lines will have a weight associated with it. And each of these neurons here will have a bias. And if you can train the network, you could probably come up with a prediction like this. Well, it's probably a 6, 50% chance it could be a 6. It also could be a 5, depending on whether this is on or off. Also, this is lighting up a bit. Maybe there's a small chance it could be an 8, but it's not going to be a 1 or a 0, because that basically wouldn't be very probable. But the key thing here, we're not making an actual decision. It's not if this is true, then take some action. If this is false, then do something else. It's basically a prediction with a certain amount of certainty there. So we do need to think about this when we're using neural networks in various scenarios. Where do we set our threshold? What is a good prediction? Can we rely on these predictions? Because they're not always going to be fully accurate. You could extend this a bit, and this is, I learned to program on a ZX81 and then a VIC-20, and we pretty much had these 8x8 characters. you can build the same logic to analyze 8x8 characters. You've got 8 pixels by 8 pixels, and you could basically build, computer logic to analyze that. And this kind of takes us on to a couple of data sets that are basically, instead of being 8x8, I think they're something like 28 by 28 characters. And they're these MNIST data sets. This is the fashion MNIST, and it's taken from, I can't remember the name of the American retailer, but there's a big American retailer that had loads and loads of photos of like, jeans and shirts and bags and all of their products. And they've been very careful to actually frame the photos. So the actual product would appear pretty much in the same place with this, and the shoe would basically appear in the same place in all of these images. So this data set was used, the images on that website were used to generate this data set, which is a very low resolution. And it's one of the standard data sets you can use to train a neural network to be able to do these predictions. So now we come on to the concept of hidden layers. With the 7-segment LED display, it would be probably fairly easy to be able to do that with, just a set of output neurons without these hidden layers. But the hidden layers are allowed to add a bit more complexity to the actual calculations that are being performed. So the actual neural network will look something like this when it's coming up with its predictions. To train these, to set all the values, we do something called backpropagation. We're actually feeding back the values and saying, well, this is an ankle boot, but it was predicting it should be something else. So let's adjust the weights and the biases to be able to actually get the prediction out that it is going to be an ankle boot. So I've got some code that does just that. If I can bring up this solution here. And I've got a couple of networks here. This is basically, the language here is Python, and the library that I'm using is PyTorch. So to do that with a fully connected network, what I'm doing is I'm basically defining my network and I'm dropping in these linear layers. So what I'm saying is the input is going to be a 28 by 28 image. So let's have an input of 28 by 28 and have 64 neurons in the first hidden layer. Then we've got another hidden layer that has 64 neurons, 64 inputs and 64 outputs. Another hidden layer with 64 inputs and 64 outputs. Then we go from 64 down to 10 outputs. The reason we go to 10 outputs is because we're predicting 10 digits. And I think this one is actually using the actual MNIST digits. I think that's the one that I'm loading. Yeah, I think I'm using the actual digits there for that one. So that's basically what a fully connected linear network will work. And you can, run and train these models and use them in very, very basic image recognition. However, these aren't going to be that great in predicting, if you've got, say, a dog or a cat in images. It's not going to be that accurate because the pixels that you're using for the inputs are all coming from the same position in the screen. So imagine if you're doing classification of these actual digits, and you can see that in some of these, this one here, the actual pixels are dark here in this image. None of these pixels are dark in this particular image. This is a completely different set of pixels, even though the shape is fairly similar. So this is a problem that where linear networks don't work too well when you're doing image classification. You imagine trying to classify photos. It's not always going to be the same pixels that are, going to be representing a cat or a dog or an owl. It's going to be different pixels that's going to appear somewhere else in the image. So we really need a very different technique to be able to actually train based on, the image can appear maybe anywhere. The item can appear anywhere within the image. It could be rotated. It could appear upside down. It could appear reflected, depending on the type of data that we are working with. So this is when we get into the concept of convolution and convolutional neural networks. Now, you probably have to go back a few years, but in school, when you were learning maths, they probably tried to teach you something called matrices and matrix arithmetic. And what a convolution layer does is it basically acts as a matrix. So this is a matrix here. It's a 5 by 5 matrix. I've tried to highlight that these values are going to be 1, and these values are going to be 0, and these values are probably going to be 0.5. Now, what we do is we take this actual matrix and we basically pass over all of the pixels in the image. So we start up here, we go across here, and then we go down a pixel and across here, down a pixel, and we go across here. And we perform the matrix operations on the actual pixels within the image. So as this thing scans across, you can see when it gets to here, it's going to start to activate because the strengths of the actual values within the matrix start to match the strengths within the image, and that will give given outputs to say that, hey, there's a straight line in this particular area of the image. And then because it's scanning the entire image, it can pick up a straight line anywhere within the image. So what this is really doing, I said edge detection, it's really line detection, it should say. If it was edge detection, then maybe it would just detect a single edge, but this is actually detecting a straight vertical line. And you could flip this by 90 degrees and you could detect horizontal lines. You could have one that detects, say, small curves. And what you're doing here is basically piecing together the actual curves and the bits of straight line and the various artifacts that are appearing within that particular image. So the convolutional networks are able to actually run with these convolutions and make better predictions on the actual networks. So I'll see if I can bring up the actual PyTorch solution. Because this second network that I've defined here is a convolutional network. And when I'm building up the network, I'm saying that instead of having a linear layer as the input layer, we're setting a convolution layer. So when I set the kernel size to 5, that basically means it's a 5 by 5 matrix that's being used for the convolution. And what I'm doing is I'm defining that we've got one input for that. We've got one channel coming in because it's a black and white image, and then we've got 10 of these actual convolutions within this. So it basically generates 10 of those actual matrices and starts scanning them over the image. And then we do another convolution layer, and then we do a dropout, and then we do a couple of linear layers at the end to do the classification. So if I run this thing, this should actually start training the actual network. And what we see is the accuracy will hopefully increase as we actually run through the training process. You can see the validation accuracy started off at 10% and then went up to 61% and then 75%. So the model is basically learning. We're training all of these layers to be able to recognize these actual digits as we go through the actual training process there. Okay, so dropping back to the slides. This is kind of what a more complex CNN or convolutional neural network will look like. You can see that there's a larger number of these actual convolutions that we've got in the first convolution layer. We then do something called max pooling, where we basically calculate the maximum values within these matrices. We're then doing another convolutional layer, and we run through several of these convolutional layers, and that will basically towards the end we then do an actual linear network there. I'm going to show some animations. I did think about coding up an animation to actually show these, but this has already been done on YouTube, and there's some fantastic animations that basically show how this process works. If I can find the appropriate page, I think it was this one here. And I'll just drop the play speed on to double so we can actually whiz through this. And what this is showing is how neural networks work internally. So this is really a single layer neural network where we're just doing the predictions on the actual values that are coming in. So you can see the actual output predictions. You can see all of the neurons inside that neural network. And then we'll move on to a multi-layer perceptron. So this is a multi-layer neural network, and you can see the hidden layers in there and how those hidden layers are basically activating as we get the image coming in. It will then, I think, move on to a convolution layer. So this is showing a convolutional neural network. And here we can see the actual convolution layers detecting and being used to actually work with the prediction. If you run through those tests, you do find that the convolutional layer does become quite a bit more accurate for being able to do predictions than using the actual single layer. So I'll drop back to the slides again, run through a couple more slides. There's another animation coming up soon. I'm just going to talk about the ways that we train these convolutional networks. I will actually show the other animation because this basically shows the complexity of a proper convolutional neural network. So this is a VGG16 neural network. This means it's got 16 layers. And it's probably one of the most basic convolutional neural networks. Sometimes these go up to like 152 layers, but this is one of the simplest ones. And it's showing doing classification of these different images. So we've got an apple, an onion, a granite, a red apple, and a kiwi. Or was it an apple? Was the first one something else? Yeah, so we've got green apple, and then we've got the onion. I'll just drop the playback speed onto double for this one as well. And we've got all of these different types of fruit that are going to be recognized. And what this animation shows is the input image running through that actual 16-layer network. So I think it's when it gets onto the actual visualization bit when it starts to get impressive. And you can actually see the number of convolution layers in one of these real-world networks. And it's showing the actual input here. It's showing the actual predicted output and what's happening in all of these actual convolution layers. And I think that was just the first set of convolution layers. There's hundreds of these and millions and millions of parameters within that network there. You can see the video just goes on for quite a while when it's just doing that visualization through all of these actual layers. And then this is showing the actual layers in action as it's actually doing the classification and what's taking place. You can see that some of them are doing things like edge detection, others are detecting other kind of artifacts in there. So as you can imagine, if you've got this many layers in your neural network, it's going to take a really, really long time to be able to train and optimize that neural network. And what people have discovered from looking at how these networks work is that different sections of the network or different layers will perform different operations. So the early layers are going to do things like edge detection, like I showed a few slides back with that 5x5 matrix that basically goes across all of the actual pixels in the image, and it detects edges, or it detects lines, or it detects curves. So earlier on, it will be doing things like edge detection and shape detection, and then deeper down in the network, remember that the simple one had 16 layers and the more complex ones can have like 150 layers. This one's got like 1, 2, 3, 4 convolution layers. So it's a very, very basic one. As we get deeper into the network, we do things like feature detection. So that will basically say, if we've got certain edges and certain shapes, and then we've got a circle, and if we've got a circle and it's specific colors, then maybe that circle is an eye. So you may be able to detect eyes within the actual network. And then towards the end of the network, you're going to do the actual classification. And so based on all of these features, all of these, say, eyes and noses and paws and whatever, ears that are appearing in the network, based on the actual positions of those and the shapes of those, you could actually say that this is going to be a dog, or it's going to be a fox, or it's going to be a cat, or it's going to be a specific breed of cat. Now, this classification is very specific to what the network is going to identify. Do you want a network that identifies certain types of car or certain breeds of dog, or is able to identify certain fruit? The edge detection, the shape detection, and say the feature detection may be the same for a lot of different scenarios. So in order to save time and save processing time, what they do is they work with pre-trained networks. So you can basically download a pre-trained network that is trained to detect edges and detect shapes and say, well, I'm just going to freeze these actual layers. I'm not going to train any of the parameters here. I'm only interested in training these layers here to do the actual feature detection and the classification. Or you could say, let's lock all of these layers and let's only train the classification layer, which would allow you to very, very quickly train neural networks because you don't have to optimize any of these parameters. And there are libraries out there you can go to on GitHub. They're typically called Model Zoo. And you can basically download these pre-trained images that are trained on, say, 100 images of, they call this COCO, like common objects in context. They're just basically trained on, say, 100 different types of images and so on, 100 different types of objects. And then it becomes much quicker to take the features and use those features to be able to train the classification. So this is how things work if you're working with the Azure Custom Vision Service. I've mentioned this quite a few times, and If you've ever created a project in Custom Vision, it basically asks you, well, we're doing a classification, I'm doing a single tag per image, and then we've got these various domains. Do I want a general domain, or do I want to go for food or landmarks or retail or various things like that? If I'm doing object detection, there's a model for detecting logos, and there's a model for detecting products on shelves. Now, if we drop back to the slides, if you have trained a model for buying a really sophisticated model for that, being able to identify products on shelves in shops, then you know, the different customers who are using that in their particular scenario are going to basically find that, well, all of the edge detection, shape detection, feature detection is going to be the same for all of these types of problems. We just need to train the classification layer to be able to do that. So what's happening in Custom Vision? When you're selecting one of these pre-trained models, if you're selecting one for food, it will have been trained on lots of items of food, and it will probably be a lot more efficient at being able to detect food. This is why it's also very, very quick to be able to train these networks. It seems unbelievable that you know, you can train one of these networks in a few minutes when it normally should take hours and hours and hours, or maybe days to train a model, because they're actually only training the last final layers within that network. And then if you're doing something like the music genre classification I demoed earlier, you might argue that, well, in this scenario, there's not that much features in here. So when I'm you know, trying to classify country music, because the spectrogram looks like this, I'm maybe only interested in taking, say, edge detection and shape detection. I'm not interested in identifying features. That's not going to help me. And when you're working in PyTorch with a framework or TensorFlow, you can actually choose how many of these layers you're going to be freezing and how many of these layers you're going to be training. Yeah, so a bit more. This is a bit of a fun project. Tess Ferenda's put me on to this. It was a project where they were looking at identifying, telling the difference between chihuahuas and blueberry muffins. So the feature identification is going to basically pick out these various items, and based on those features, you're able to actually train, you know, what the actual model, what the actual item is within the photo. And then they got all of these weird photos. Well, are these chihuahuas or are these blueberry muffins? Which is which? They look very similar because the network is getting confused over which is which. And humans probably, if you stare at these, you could probably tell the difference between all of these. You probably get all of them right. However, neural networks have a really hard time when you give them data like this to actually do classification with. Yeah, I think I've already covered the stuff. So what I'm going to get on to now is generative AI. And pretty much everything we've been talking about in this whole series on machine learning and artificial intelligence, we've been doing something called dimensionality reduction. So the input is going to be an image. There's lots of information there. There's lots of pixels. There's a really high volume of data. And we're basically distilling that high volume of data down to a much lower volume of data. So the input is going to be a photo, and the output is going to be a group of people sitting at a table using a laptop. Now, what generative AI does is it basically turns that completely upside down. And it says, well, let's do it the other way around. What we're going to do is send in a sentence, an illustration of a baby daikon radish in a tutu flying a kite. And we feed that into the neural network, and it's going to come out with this, the actual image. So it's basically doing it the other way around. I didn't believe it when I first saw that. However, there is a website. I'll drop it in the YouTube chat, actually, because it's fun to play around with. Please don't go away from the session and start playing around with it now. Where is it? Where's my... That's not it. Yeah, it was in here, the DALI project here. So what we can do is saying an armchair in the shape of an avocado, and or an armchair imitating that avocado. So what we can do is change it to a coffee table in the shape of a donut. And it's actually generating, you know, photo quality images of a coffee table in the shape of a donut or in the form of a donut. And these aren't, it's not basically doing an image search and finding images. These images have been generated. They don't exist in reality. unless you actually build one of these, this object doesn't actually exist, and it's able to just create these things. A soap dispenser in the shape of a donut, and it's able to come up with these types of images. There's all types of good fun and good exercises taking place with generative AI. Well, how does it work, and how can we actually leverage it to do these dancing videos? Because this is kind of based on similar techniques. So if I drop back to the slides, it started off with an AI which was called Pix2Pix. And what they've done is they've trained Pix2Pix on various data sets to be able to increase the dimensionality of an image. So one of the examples is this, which is basically a bunch of boxes. We've got a door, we've got some windows, we've got a roof, and we've got some facade, and that's basically able to generate an image of a building. And based on the actual data sets, they're able to actually, take an aerial image and be able to convert it to, I think I've got those the wrong way around, actually. The input should be the actual street map, and the output is going to be the actual terrain. So they've trained it on lots and lots of data from Google Maps by taking the actual map image and the aerial photo, and then it's able to generate aerial photos from an actual map image based on all of those options, all of those scenarios. So other scenarios is being able to convert day to night, get lots of photos of the same scene by day, same scene by night, and then it can auto-generate that. Being able to take edges and be able to generate them to photos is another example of that. So we've also got this available online. I'm going to save these links to the end so you don't go away and play on them. Yeah, somebody was just saying feature extraction is only effective if there is a similarity between the data set of the trained network and a new one. Yeah, it's really hard to say how effective the feature extraction is because there's so many layers, like 150 layers or something in the network. It's really hard to say that this layer will detect certain features, or this will detect that. It's mostly trial and error when you're freezing the layers and seeing if it gives quicker training to be able to get more accuracy in that. So it really depends on the actual scenario. And a lot of experimentation has to be done as well. It's not really a set of rules that you can be adhere to. So the Pix2Pix website is here, and there's various things that you can play around with. So you can randomly take these cats, and you can actually modify these images here. So this one here, the cat only has one eye. It always seems to go a bit clunky when I do that, but I'm going to try and draw another eye on that and then process that and see if it will actually draw the other eye on the cat. Oh, it didn't work too well on that one there. Let's try another one. I'll try that one again. I'm not an artist, but we'll see what that one does. Oh yeah, it has actually drawn two eyes on the actual cat from that line drawing. And there's the example with the building. You can basically clear this, and then you can maybe draw a couple of columns, and then put a door in, and a couple of windows, and process that. And all of these examples is what I've been mentioning about increasing the actual dimensionality. We're going with a low information, and it's generating high information there. So there's plenty of these you can play around with and look at how those work. Pix2Pix is fairly basic, but Pix2Pix is really at the heart of where the Everybody Dance Now AI is going. So if you think about Pix2Pix, what we're going to do is think about doing actually training to actually get towards this dancing demo. So basically, I think I mentioned earlier on that you can take the input data and you can use a network to be able to detect poses within that. So the idea is that we're going to take this pose data and we're going to use the same type of technique in Pix2Pix. We're going to increase the dimensionality of that pose data. And that's actually going to generate the image of a person, that's my son James, in the actual position of that particular pose. So this network is going to be trained with lots of images of James and lots of images of the actual pose detected from James. I think I should be able to find these images somewhere. I think I actually do have the data sets on my machine. Let's see if I can find them. Yeah, so this was the actual images that I used from James. There are, I think there's just 99 images. This is a very, very small data set. You should really be using thousands of these images. So if I open this with photos, I've actually shot it on a green screen as well. You can see all of the actual images there of James in those positions. And we run this through the actual pose detection video. AI, and that will basically come out with the actual labels for this. So if I open these in photos, you can basically see the actual pose pictures there, and each one of those corresponds to a frame within the particular video. So that's how the model is trained. We're training this model to take this as an input and give this as an output. Then what we can do is take somebody who can dance, like Bruno Mars, and then basically use the Open Pose AI to be able to generate a whole series of these actual pose images from a professional dancer. What we do then is basically feed these into the Pix2Pix network and basically get James dancing alongside Bruno Mars. So that's really the theory of how this works. We'll go into a bit more depth about how the theory works. A couple of things I found really useful. A really big green screen is useful to have. Also, this book, Hands-on Generative Adversarial Networks with PyTorch. The actual technique we're using is called a GAN, or a Generative Adversarial Network. And so that's basically the setup I had at home. I got a green screen and I was basically filming against that. I used a Samsung S20 or something like that, or S21, fairly recent Samsung, and I was filming at quite a high resolution. I also set the frame rate to 120 frames per second. The reason I did that is I wanted to capture a really large volume of training data. So this, allows you to capture a lot more input images. And I don't know if I've got the actual data set I was using for myself. No, I think I closed that. I'll bring it up again because that had a lot more data in it. Yeah, when I was training it with myself, I had 21,600 images there for the actual labels, and then with the images there was 21,600 images as well. So I was using a much higher volume of data when I was actually training it on a real model. So creating the source data, we take the actual video and then about 3 or 4 lines of Python. You can actually split it out into all of the individual images, and you do need a large hard drive. It does generate a lot of data from these actual images. We then use the Open Pose AI, and that basically generates these actual stick figures, which is your training data. Then going to be training the model. This is where it takes time, depending on the GPU you've got. If you want to do this at home, you need a pretty big GPU because the model will take about 16 gig of GPU RAM. So if you've got, a sort of really high-end, 3000 series RTX card, that's probably going to work. If you've got, say, a laptop GPU with only 4 gig of GPU RAM, it's not going to be able to load the model. You'll just get an out-of-memory exception. So Azure ML does allow you to actually deploy to those actual machines that do have the actual GPU. For generating the target data, you do the same thing. You take Bruno Mars, you put him through Open Pose, and you get out the target poses for Bruno Mars. Then the actual transfer process, you're taking the target poses and they're going through to actually generate the actual images there. I've got to hunt around for that actual video because I did download it this morning. I'll see if I can find it. Yeah, I saved it. Oh yeah, I think I've stuck it in the videos on the AI files. I'm really scared that the video doesn't get blocked with copyright. I don't want to show anything that's not legal, so I'll try and hide it from the screen when I show it. Yeah, so I'm going to have to be a bit careful when I do this. Okay, yeah, so see if I can bring this up onto the screen. So what I've got here, I'll try and hide off the Bruno Mars because that's probably copyrighted. This is the actual target with James dancing, and then there's the actual source video. And what I was doing is actually mapping, using Bruno Mars pose to be able to generate James dancing in the style of Bruno Mars. The quality isn't that great. There's a couple of things that have affected the quality. The first one is the amount of training data. Try as I might, it's hard to get James to do something, a single task for a long time. So he got bored of trying to dance like Bruno Mars fairly quickly. So I didn't really have that much training data to use. Also, the training model time. I think I trained for about 48 hours to actually produce this image there. I think it takes maybe sort of 50 or 100 hours to actually train it with a really to get much higher quality. You've seen when you look at the Everybody Dance Now stuff on YouTube that the quality is a lot higher. They have actually managed to train the models, and it does take a lot of time. The options there aren't that great. I do have a nice machine at home with an RTX 3090. However, running that thing for 5 days isn't very popular at home because when we're downstairs in the bedroom, you can actually hear the GPU fan up running, and electricity isn't too cheap in Sweden right now, so it does get very, very expensive. I think the GPU card itself takes about 350 watts, and the computer's probably taking about 500 watts, so it does cost quite a bit. Running it in Azure ML is a good alternative. It's not going to cost you that much because you can take advantage of these low priority virtual machines. And you can actually provision a machine. I think it was about 75 cents an hour to be able to run on one of the really high performance GPUs, running on a low priority pricing, which basically means that you want to start the job. It may not start immediately, but maybe after about 8 or 12 hours, you'll get access to a machine because you're paying a much lower price there. And looking at the code, it's just a case of taking the code from GitHub and throwing it up into Azure ML. So I'll see if I can bring up the solution for it. And the Everybody Dance Now code is available on GitHub. It is a bit of a fight to get it to run on your local PC. You've got to install all of the Python bits, but this is basically how I've built it. So what I've done is I've taken the Everybody Dance Now code from GitHub and dropped that there, and I've basically got the code to be able to run this in Azure ML if I can find it. Yeah, I think that's it. Yeah, so this is the actual code to get it to run in ML. So what I'm doing is I'm basically spinning up a GPU cluster on low priority, and I'm creating a Python environment. The environment is a YAML file, which basically looks like this. So I'm saying, okay, we're using Python version 3.7, and this is the stuff that we need to install. We need to have PyTorch. We need to have various things running on the GPU, and these are the various libraries that are going to be installed. It will prepare that environment and then run the actual code on that and train the model. I think it took the most high quality model I trained took about 168 hours to train in Azure. So it is a fairly quite a long training time to be able to get that. But the thing that struck me was just the ease of being able to take the GitHub code and get it to run in Azure ML without making too many modifications to the actual code. As far as the training process goes, the quality does improve over time. I think I've got some slides that illustrate this. Yeah, so what happens is when you get through the actual first training iteration after, say, 30 minutes or so, the output image looks like this. And the way that this works is we're generating the image, and you have another image called a discriminator, which will say, how good is this image compared with this particular image here? And it will basically give it a score. And the idea is that the generator is going to improve in quality, and that's going to be, generating better quality images. Also, the discriminator in the training process, he's also getting better at being able to distinguish between the fuzzy output and the actual real image. And these are working. It's kind of an adversarial technique where these two networks are competing with each other. The generator is trying to create better quality images and get better at doing that, and the discriminator is becoming better at being able to distinguish between these fake images and the real images there. As we go through the training process, you basically see the quality of the image improving over time until it does get to some reasonable level of quality. Another thing that the Everybody Dance Now stuff does is temporal coherence, where instead of training just on one image, what they're doing is they're training on the image and they're training on the actual current frame and the previous frame, because there is motion involved here. And in order to get the motion looking more realistic as well as the images looking more realistic, if you train it on 2 frames, it does actually do a better job of being able to actually work with the motion. Obviously, there's going to be a lot more training data there to be able to actually generate those images there. So it is going to take longer to train on those options there. Okay, so I won't mention too much about the other stuff. I think we're getting towards the end now. So I think I'll just sign off and take any questions if anybody has any. I'll actually share the links to the resources that I mentioned if I've still got those open. So I'll give you the link to the dolly if you do want to play around with that, and then the link to the image to image demo with Pix to Pix. Please feel free to ask in chat if you do have any questions.
Are you dropping the links via YouTube or?
Yeah, I've dropped them in the YouTube chat.
Okay, all right, because then they will show up. So yeah, thank you for another fantastic session, Alan. And dear audience, if you have questions, please ask them now. I think you have answered Srini's, right?
Yeah, I think so. Yeah.
Okay.
Yeah, I did. Yeah.
I don't see the links you have dropped showing up.
You don't see them?
No, I don't see them.
In the YouTube chat? That's strange. I'll drop them in.
Drop it, just in case, drop it in the private chat to me, and then I can also drop it here in the chat, because I can't see them. I don't know if our audience sees it.
I'll drop them in the private chat, and then you can drop them on the in the description.
We'll do that. Nope, they don't see it either. Okay.
That's strange.
Okay. It's okay. We have a solution for that.
Yeah, I see them here. There, when I type in, it appears here.
And you don't get any error message, right? Like that. It's
No,
not.
no. Maybe I'm banned or blocked or something. They don't like
me. Yeah, it was just these two, right? So yeah, guys, I've dropped it in the chat now. Srini is asking if we get your presentation. That is up to you, Alan.
Yeah, I don't normally share the slides because my slides tend to be a bit of a work in progress, and I'm always hacking them and changing them. So I don't normally share them.
Okay, that's absolutely fine, of course. Any other questions? No questions now. No? Come on, guys. Ask them now or never, or next week. Actually. Yeah, in the meantime, I will bring up my my screen and let me here. Yes. So yeah, today was the 8th of March, and next week we are going to welcome Alan back, where he's going to be. Oh, that's a nice title. Do you want to say a couple of words about it, maybe, Alan?
Yeah. It's a gaming AI, and what I'm doing kind of follows on a bit from the session I did with Eve Padre a few weeks ago when we were talking about the evolutionary AI and gaming. But this I'm going to be focusing on the game StarCraft and being able to actually use Python to be able to generate AIs that will evolve and learn to play StarCraft. I was inspired by, there's a YouTuber, I can't remember his real name, but his YouTube channel is called Centex, and he's done some quite a lot of series with working with StarCraft, and he's just I think last week he started a new series on working with StarCraft AI. So I've been watching that, and I might need to update that. Yes, it's going to be at reinforcement learning. I'm going to be looking at using genetic algorithms and focusing on using a genetic algorithm for the build order. So if you've ever played StarCraft, it's really important how you start creating your units right at the beginning of the game. And what I do is basically use a genetic algorithm to be able to evolve a build order, to be able to, you know, build a certain amount of resources or build a certain amount of military in the shortest possible time. And then that can be used to be able to play against the actual computer and see if you can defeat the computer in StarCraft with an AI that's basically learnt how to build units.
Fantastic. Thank you. Looking forward to that. You have had a reinforcement learning session on season 1 with Eve Party.
Yeah.
This is like a next step, I guess.
Yeah,
right?
Yeah. There's going to be a lot more code in this one.
Yeah, great. And then the third episode on season 2 is synthetic data from 3D model to AI on the edge. And we are going to be welcoming another AI MVP from Sweden, Göran Vucic. I think that's how he pronounces his name. Maybe Ellen, you can help me. Oops, sorry there. Yes, thank you so much, guys. I don't think we have any questions. Mark says that he's appreciating that you're walking us through that. Let's move back here. Yeah. So yeah, guys out there, I see you next week. And yeah, we have no more questions. So with that, I will let you go, Ellen, now. And yeah, I see you next week. And actually, I see you tomorrow for the Cloud Native as well. So yeah, thank you so much for today. And I will see you soon. Guys.
Excellent. Great. Thanks. Bye. And thanks for everyone for joining.
With us today. Thank you. Bye.